If you're a student or beginner trying to understand IT, information systems, or programming without the confusing jargon, welcome to LD Tech Lab. Make sure to subscribe, and let's break this topic down step by step.
Welcome everyone to our session on data structures and algorithms for beginners. This is one of the most important topics you will learn because it helps you transition from just writing lines of code to truly thinking like a professional programmer. We are specifically looking at this from the perspective of senior high and college students. While we will use Python and Java for our examples, the logic we discussed today applies to almost every programming language out there. Today we are going to cover everything from the basic introduction and algorithmic thinking to more complex topics like big O complexity. We will also look at different types of data structures and wrap up with some real projects you can build to practice what you have learned. A data structure is basically just a way of organizing and storing data so that it can be used efficiently. You can think of it as a container designed for a specific purpose. To make it easier to understand, think of a filing cabinet as a structure for documents. Boxes on a shelf are like an array because items are stored side by side, and a stack of plates represents a stack structure where you only take from the top. The right container makes finding your data much faster. An algorithm is a step-by-step set of instructions used to solve a specific problem. It is very much like a recipe in a kitchen where you follow the steps to get the same result every time. For an algorithm to be considered good, it must be correct, it must eventually end, and it needs to be clear without any confusion. It also needs to be efficient so it does not waste the computer's resources. Think about making a peanut butter sandwich. You have to get the bread, open the jar, spread the peanut butter, and then close it. Computers follow similar logical steps to search for information or sort a list of names. The main difference is that a data structure is how you store the information, while an algorithm is how you process it. They work together because an algorithm always operates on a specific data structure. Another way to look at it is that the data structure is the house itself, which provides the organization and storage. The algorithm is like the process of cleaning the house, which represents the action being taken. Take a phone book for example. The phone book itself is a sorted list, which is the data structure. The act of looking up a specific name is the algorithm, such as using a binary search to find someone quickly. This matters because good data structures and algorithms can make your code run over 1,000 times faster. It also prepares you for a career since top companies test these skills, and it helps you understand how real systems like apps and games work under the hood. You can see this in action every day. Search engines use trees to index pages, social media apps use graphs to rank your friends, and navigation apps like Google Maps use shortest path algorithms to find your route. A good algorithm must produce the right answer for any valid input and must stop after a finite number of steps. Each step has to be clear and unambiguous so the computer knows exactly what to do next. Before we write actual code, we use pseudocode. This is just writing the algorithm in plain English. It does not have strict rules, which allows you to focus purely on the logic and steps required. For example, if we want to find the largest number in a list, we start by looking at the first number. We then check every other number in the list and update our record if we find something bigger until we have the final answer. Efficiency becomes a problem when data scales up. Searching through 10 names is easy for any method, but searching through 1 billion users on Facebook requires a fast algorithm to avoid taking hours. Imagine looking for a friend in a crowd. A bad approach would be checking every single person one by one. A good approach would be just calling their phone, which gets the job done instantly regardless of how many people are there. We use big O notation to measure how the runtime of an algorithm grows as the input size increases. We usually focus on the worst-case scenario to understand how bad the performance could get. There are several categories like constant time, which stays the same speed regardless of size, and linear time, where the speed grows directly with the size of the data. We also have quadratic time, which often involves nested loops and grows very quickly. Think of constant time as finding the first page of a book. Logarithmic time is like guessing a number by constantly halving the possibilities, and linear time is like reading every single page to find a specific word. Arrays are the basic building blocks. They are fixed-size collections where items are stored side by side in memory. You can access any element instantly if you know its position or index. In both Python and Java, Accessing an item at a specific index is a very fast operation. You use arrays when you already know the size of your data and need to access things quickly by their position. Lists or array lists are more flexible than standard arrays because they can grow or shrink automatically. They are perfect for things like shopping carts or to-do lists where you do not know the final size in advance. A stack works on the principle of last in, first out. Think of it like a stack of plates where you can only add or remove from the top. This is used for things like the undo button in your text editor. In Python, we can easily use a list as a stack. We use append to push a new item onto the top and pop to remove the most recently added item. A queue follows the first in, first out principle, just like a line at a fast food counter. The first item added is the first one to be removed. This is very useful for scheduling tasks or managing print jobs. A linked list is a sequence of nodes where each node points to the next one. It is like a treasure hunt where each clue leads you to the next location. It is more flexible than an array but slower when you need to search for something. A tree is a hierarchical structure that flows downward from a root to its children and leaves. Binary trees are common, where each part has at most 2 children. We use these for things like file systems and databases. Graphs are sets of connections between points. Unlike trees, graphs can have cycles and multiple connections between nodes. They are used to model social networks and maps. Hash tables store data in pairs to allow for lightning-fast lookups. It is like having a magic dictionary that lets you open to the exact page you need instantly. This is used for login systems and caches. Linear search is the simplest way to find something by checking every element from left to right. It is slow for large data, but it works even if the data is not sorted. Binary search is much faster because it splits the list in half with every step, but it requires the data to be sorted first. It can find one item in a billion with only about 30 comparisons. Bubble sort is a simple way to organize data by comparing neighbors and swapping them if they are in the wrong order. It is easy to understand but not very efficient for large amounts of information. Selection sort works by finding the smallest item in the unsorted part of a list and moving it to the front. You repeat this until everything is in order. It is simple but can also be slow as the list grows. In this practical example, we can see how a stack is used to create an undo system. Every time you perform an action, it is added to the history, and clicking undo simply removes the last action from the top of the stack. For a task scheduler, we use a queue to manage print jobs. New jobs are added to the back of the line, and the system always processes the job that arrived first. You encounter these concepts every day. Social media feeds use graphs, navigation apps use shortest path algorithms, and your operating system uses priority queues to decide which task to handle first. Your first project could be a student record system. You will learn how to manage, search, and delete records using basic lists and searching algorithms. Another great project is building a simple text editor with undo and redo functions. This will give you hands-on practice using the stack data structure and the principle of last in, first out. You can also build a task scheduler app. This will help you understand how queues work and how systems prioritize different tasks based on when they arrive. A contact search system is a perfect way to learn about hash tables. You will see how you can achieve instant lookups even as your list of contacts grows larger. For a more advanced challenge, try a mini navigation system. This will teach you how to represent maps as graphs and how to find the shortest route between 2 points. Common mistakes include choosing the wrong data structure or ignoring efficiency. It is also a mistake to overcomplicate things or forget to test how your code handles empty or very large lists. To master this, always start with a simple solution before optimizing. Write your plan in English first, visualize your structures on paper, and practice consistently with daily problems. Today we covered the basics of data structures and algorithms, how to measure complexity with Big O, and several real-world applications. These concepts are the foundation of every app and game you use. Your next steps include learning about more advanced structures and practicing for coding interviews. Remember that every expert started as a beginner, so keep coding and keep thinking.
If this video helped you understand the topic better, please like, subscribe to LD Tech Lab, and comment below what you want to learn next. Your questions help shape future lessons.